we are told the population of a town grows at a rate of e to the 1.2t power minus 2t people per year, where t is the number of years. At t equals 2 years, the town has 1,500 people. So first they ask us approximately by how many people does the population grow between t equals 2 and t equals 5? And then what is the town's population at t equals 5 years? And if we actually figure out this first question, the second question is actually pretty straightforward. We figure out the amount that it grows and then add it to what we were at t equals 2. Add it to 1,500. So pause this video and see if you can figure it out. So the key here is to appreciate that this right over here is expressing the rate of how fast the population is growing. And we've been seen in multiple videos now. Let me just do a quick review of this notion of a rate curve. So if those are my axes, and this is my t-axis, my time axis, and so this is showing me how my rate of change changes as a function of time. So let's say it's something like this. So once again, if I said at this time right over here, this is my rate, this doesn't tell me, for example, what my population is. This tells me what is my rate of change of a population. And we have seen in previous videos that if you want to figure out the change in the thing that the rate is that the rate is the rate of change of, say, the change in population, you would find the area under the rate curve between those two appropriate times. And why does that make sense? Well, imagine a very small change in time right over here. If you have a very small change in time, and if you assume that your rate is approximately constant over that very small change in time, well, then your change in, let's say we're measuring the rate of change of population here, your accumulation, you could say, is going to be your rate times your change in time, which would be the area of this rectangle. And so that would be the area under the curve over that very, very small change in time. So what we really want to do is find the area under this curve from t equals 2 to t equals 5. And we have seen multiple times in calculus how to express that. So the definite integral from t is equal to 2 to t is equal to 5 of this expression of e to the 1.2t minus 2t dt. So if we just evaluate that, that will be the answer to this first question. So what is this going to be? Well, let's actually work it out. So what is the antiderivative of e to the 1.2t? Well, let me just try to do it over here. So if I am trying to calculate, let me write it as e to the 5, or actually 6/5 t. Say 12/10 is the same thing as 6/5. 6/5 t dt. So this is an indefinite integral. I'm just trying to figure out the antiderivative here. Well, if I had a 6/5 right over here, then u substitution, or sometimes you would say the inverse chain rule, would be very appropriate. Well, we could put a 6/5 there if we write a 5/6 right over here. 5/6 times 6/5, and we can take constants in and out of the integral like this. Scaling constants, I should say. Well, now, so this is going to be equal to 5/6, this 5/6 right over here. This antiderivative is pretty straightforward. Since I have the derivative of 6/5 t right over here, I can find the antiderivative with respect to 6/5 t, which is essentially I'm doing u substitution. If you had to do u substitution, you would make that right over there u, and that would be your du. But needless to say, this would be 5/6 times e to the 6/5 t, and if you're thinking about the indefinite integral, you would then have a plus c here, of course. And you can verify that the derivative of this is indeed e to the 1.2t. So this is going to be equal to, so this part right over here, the antiderivative, is 5/6 e to the 6/5 t. And then this part right over here, the antiderivative of 2t is t squared, so minus t squared. And we are going to evaluate that at 5 and 2 and find the difference. So let's evaluate this at when t is equal to 5. Well, you are going to, let me color code this a little bit. When t is equal to 5, you get 5/6 times e to the 6/5 times 5 is e to the 6th minus 5 squared, so minus 25. And so from that, I want to subtract. When we evaluate it at 2, we get 5/6 e to the 6/5 times 2 is the same thing as 12/5, or we could say that's 2.4. 2.4 minus 4. 2 squared is 4. And so what do we get? Well, there's a couple of ways that we could do this. So that we could write this as, let me write it this way. We could write this, so we have a 5/6 and a 5/6. So we could write this as 5/6 times e to the 6th, minus e to the 2.4, minus, because we distribute that negative sign, e to the 2.4, e to the 2.4 power. And then we have minus 25. Let me just in another color to keep track of it. We have minus 25, and then you have minus negative 4. So that would be plus 4. So that would be minus 21. And I would need a calculator to figure this out. So let me do that. Let me get my calculator on this computer. And there we go. And so let's see. If we want to find e to the 6th power, that's 430. Okay, so now let me figure out. So minus, I would say 22.4. That looks like a 24. I'll correct it as soon as I get back to that screen. E to that power, e to the 2.4 power, and I get equals. So what's in parentheses is this number right here. So times 5/6 times 5 divided by 6 is equal to that minus 21 is equal to this. So if I round to the nearest hundredth, it's going to be approximately 306.00. So this is approximately 306.00. So approximately by how many people does the population grow between t equals 2 and t equals 5? Well, by approximately 306 people. Let me write that down. So approximately 306 people. And they say, what is the town's population at t equals 5? Well, at time 2, at 2 years, we had 1,500 people. And then we grow over this interval by 306. So plus 306. Well, that's going to get me to, deserve a little bit of a drum roll, 1,806 people at t equals 5 years.